Greetings and welcome to the complete lecture for Chapter 8 of Chemistry 222. And in this chapter, we're going to see where modern chemistry started, which was with the study of gases. And when you think about that, that's incredible because gases are so hard to contain. I mean, you have a small leak in your system and the gas is gone. But anyway, way back in the 1700s and early 1800s, this is how chemistry got its start. They started to model the behavior of gases using math and apparatus, which is pretty cool. So let's check this chapter out and see what this section has to offer.
In a collision involving a car equipped with airbags, the impact initiates a chemical reaction. Automobile airbags work when a sample of sodium azide detonates, producing nitrogen gas. This gas fills the bag. Using our understanding of the gas laws, we can calculate the quantity of sodium azide required to produce the appropriate amount of nitrogen gas.
A lot of people know people that have been saved in a bad car wreck because of airbags, and I have family members that have been saved by this too. And airbags are a direct result of scientists' understanding of the gas laws. In the airbag is usually a sodium azide. That's that NaN3 thing down there. And it's a solid, but it can be disturbed, and it ends up making sodium metal, but more importantly here, nitrogen gas, N2. And the gas is what expands. It creates like a cushion so that you and your body don't get hurt too bad, which is incredible. So gas laws are definitely important, and they've saved a lot of people over time.
According to the kinetic molecular theory, the molecules of a solid are locked in place, though they have motion. Molecules of a liquid are closely associated with each other, but move relative to one another. Molecules of a gas move independently and occupy a much larger volume than those of a corresponding liquid or solid.
So as a reminder as to how chemists see the differences between solid liquids and gases, I'll remind you about what's called the kinetic molecular theory, the KMT. And that basically states that solid molecules are locked in place and they don't move around very much. At 0 Kelvin, even that movement would stop, but there's always some movement in solid. Liquids, on the other hand, there's a connection between them, but it's a lot less rigid than the solid. So liquids do stay together, but you can pour them and they'll take up the volume of the space that it occupies. Gases, on the other hand, there's no interactions between them at all. All right, they kind of move around on their own. They collide into each other, but it's no big deal. So you can see the differences here. Now, again, it's important to remember that solids, liquids, and gases, it's all the same. So if we're talking about water here, ice would be the liquid version of water at a low temperature, so that's why it's solid. Liquid water would be, of course, drinking water, and then gas would be steam. So those blue molecules in this model would represent H2O. It's just the interactions between the H2Os which are different that make solids different than liquids, which are different than gases. We're going to look at gases in this chapter a lot. In the next chapter or so, actually a couple chapters, I guess, we will look at solids and liquids in more detail. Now, in addition to solids, liquids, and gases, there is a fourth state of matter called plasma. And plasma in the universe is the most common phase of matter. We'll look at plasma in chapter 20, but it's not super common on the Earth. Well, again, we'll talk about that more later, but I just wanted to tease you. Check out the little pictures of the sheep up there. Those are great representations of gases, liquids, and solids. So in gases, the sheep are just all over the place, no control. Liquids, on the other hand, you can see they're all kind of trying to get through that one little area right there. That would be liquid flowing through a container. And on the other hand, solids there are hanging out very tightly together. All right, I have a strange sense of humor. Now, when you talk about gases, you must talk about the pressure. And pressure is something we haven't talked about before. But from physics, pressure is basically the force exerted on a given area. All right. And there's a lot more to pressure than we'll talk about, but we'll talk about pressure as it relates to gases. Now, what's interesting about pressure is that it was first explored by Torricelli and other Italian scientists in 1643. So that's quite a while ago. And Torricelli was the person who's given credit for developing the barometer. And the barometer is a measure of the pressure of a gas. Now, it was usually for atmospheric pressure, but you can use a barometer for all different kinds of things. Now, in a classic barometer, which is shown there on the right, you have a pool of mercury on the bottom and a tube with a vacuum in it on the top. And the pressure of the air forces the mercury up the column. Now, eventually, gravity starts to pull the mercury back down. So there's a place where the gravity overpowers the atmospheric pressure. But as the pressure goes up and down, that empty space in the top goes up and down, and you can literally read the length that the mercury goes up the column. And so if you are at 1 atmosphere of pressure, the length of the column will be 760 millimeters of mercury, which you can measure with just a ruler or something like that. Barometers have to be calibrated for the pool width and depth and the mercury density and lots of other things. And you don't have to use mercury, but it's a lot easier because of the density. We'll maybe talk about that in class more. But anyway, this is a barometer, and they have now, of course, electronic versions, but the classic mercury barometer is still seen as the gold standard for determining the gas pressure at any given moment. If you're measuring a barometer, the classic way is to measure from the depth of the mercury pool to the top of where the mercury column stops. And if you're at a standard atmosphere, which is like normal atmosphere, that's equal to 760 millimeters of mercury. And that's a conversion we'll use a lot. 760 millimeters of mercury equals an atmosphere. Now, as you know, there are 10 millimeters in a centimeter, so sometimes you see these listed as centimeters. That would be 76 centimeters of mercury for an atmosphere. A torr is a unit that's basically an homage to Torricelli, and a torr is the same as a millimeter of mercury. So if you have a standard atmosphere, that would be 760 torr. So a torr and a millimeter of mercury, same thing. There's another unit called a millibar that we will use once in a while. 1,013 millibars equals 1 atmosphere. We'll use this in lab. Some of our devices use millibars, so make sure you make a note of that. On the other hand, sometimes if you're watching news, they'll talk about so many inches of mercury when you're talking about weather. 29.9 inches of mercury is equal to 1 atmosphere. And again, we won't use that here in this class, but if you're watching the news, they'll talk about differences in barometer pressures, and they're always right around 29.9 or so inches of mercury. Now, mercury isn't the best element to use because it is kind of toxic, so you can use water. However, the density of mercury is about 13.6 grams per centimeter cubed. If you wanted to use, for example, water, which is 1 gram per centimeter cubed, the tube will be a lot higher. So you need to have about 34 feet of water to measure if you're going to measure an atmosphere. And having a tube that's 34 feet tall is not very useful when you're in the laboratory. Now, it is more accurate. You can definitely measure very small, minute changes to atmosphere, but you have to have like a multi-story level where you can put this water-based barometer out. And I saw one at a school I was at one time. It was fantastic, but again, you have to have very special kind of conditions. Now, the SI unit for pressure is called the Pascal, and 1 atmosphere is 101.325 kilopascals. A millibar is equal to 1 hecapascal, which is another metric unit. We won't use the Pascal too much, but in physics you might. So if you take physics and you want to relate all the things we're talking about, just FYI. The ones we're going to use a lot in this class are 1 standard atmosphere equals 760 millimeters of mercury, or 760 torr, same thing. We'll also use that 1 standard atmosphere is equal to 1,013 millibars. So those are the ones that we'll use in this class more than the others. Here's a question you might see. It says nitrogen gas has a pressure of 452 millimeters of mercury. What is the pressure in atmospheres? So what you would do here is 760 millimeters of mercury equals an atmosphere. That's a conversion factor. So you would take 452 millimeters of mercury. You would divide by 760 millimeters of mercury per atmosphere. The millimeters of mercury cancel out. You're left with atmospheres. 0.595 atmospheres is the answer you'll get. Atmospheric pressure is supposedly the pressure that you would experience if you're right at sea level. So if you go to Seaside, Lincoln City, Newport, one of those kind of places here on the Oregon coast, you should experience a pressure of about 1.0 atmospheres. However, as you get higher in elevation, then you start to have lower pressures. So for example, if you go to Timberline on Mount Hood, which is about 6,000 feet, you would experience a pressure which was less than 1 atmosphere. And even here in Gresham, Oregon, where the elevation is supposedly about 300 feet, you will experience less than 1 atmosphere. However, this does not take into account storms. Storms will make the pressure go up and down, and it's kind of fun to monitor the pressure as you go through. So people talk about the mile-high city Denver. You can see in that picture the pressure is about 0.83 atmospheres. On the other hand, in Bolivia there, which is much higher, 0.62 atmospheres, and the top of Mount Everest, 0.35 atmospheres. If you've ever watched the movies of people climbing Mount Everest, a lot of times they have oxygen masks because the oxygen level is so low, they can't get the oxygen to climb, so they have these special kind of portable oxygen containers to keep themselves going, which is just fantastic. Scientists wish to relate pressure, definitely, as well as volume and amount, which will be moles, and temperature to gases. And there's many different ways to do this, but what's usually used is what's called the ideal gas law. And the ideal gas law is just a great way that sums up all the different changes that you might experience while studying gases. So when it comes to any sample of gas, this could be water vapor or methane, natural gas, carbon dioxide, etc. You have to consider the pressure of the gas, the volume of the gas, the temperature of the gas, and definitely how much gas you have, which scientists will use the mole. Now, here are some units that are going to be super helpful in this section we're getting into. For pressure, once again, 760 millimeters of mercury equals 1,013 millibar, which equals 1 atmosphere. They're all the same. And also a millimeter of mercury and a torr are the same thing, so you can interchange those units. For volume, 1,000 milliliters equals a liter is going to be very, very helpful to us. And remember that a milliliter and a centimeter cubed are the same thing, so we'll go back and forth between those. We're going to interchange Celsius to Kelvin in temperature a lot. You add 273.15 to the Celsius temperature to get the Kelvin temperature. And then finally, we will talk about the moles of gas. A lot of times you'll need the molar mass of the gas. So from the periodic table, you can find the grams per mole of, say, helium, or the grams per mole of, say, water. You can turn the grams into moles and be good to go. Guy Lussac, I may be totally mispronouncing that name, and I apologize to that scientist. But anyway, he was the one that figured out that there's a temperature dependence on the pressure of a gas. And if you use Kelvin temperature, and you must use Kelvin, then the pressure is proportional to the temperature. So as the temperature goes up, the pressure goes up. And as the temperature goes down, the pressure goes down. Now, Kelvin is the ultimate way to use this law, and I highly recommend that in this section you always convert any Celsius things you see into Kelvin. Celsius values can be negative and 0, so that's why we have some problems with the math. But anyway, you can see there, even though that pressure is in kilopascals and not atmospheres, you can see that as temperature goes up, i.e. go down the column, then the pressure goes up as well. This is the idea. The K value there is a constant. So what scientists will do is they'll have two sets of conditions, a pressure one and a temperature one, and then a pressure 2 and a temperature 2. And when you figure it out, P1 over T1 equals P2 over T2. You can graph pressure versus temperature, and that graph in the lower right there, it's a nice linear line, which is kind of cool. Oh yeah.
Temperature and volume are directly related. As heat is added to a sealed syringe, the volume of the air in the syringe increases. A plot of gas temperature and volume demonstrates that the relationship between them is linear. If we extrapolate the line down to a temperature of absolute 0, in principle, the gas has no volume.
Charles' law. Charles was another scientist that did work a long time ago on different gases. But anyway, Charles's law relates volume to temperature. And just like with pressure, as the temperature goes up, the volume will increase. And as the temperature goes down, the volume will go down. And like with pressure, you can get the V1 over T1 equals V2 over T2 expression, which is really cool. So this is Charles' law. And by the way, you don't need to know the names of these scientists, but of course, the mathematical relationships of all these will be important. So I won't ask you like what's Charles' law or what's Guy-Lissac's law, but I will ask you questions about volume and temperature, pressure and temperature, stuff like that. One interesting thing about Charles' law is that if you extrapolate that data all the way back to 0 Kelvin, which is absolute zero, you can see how in theory the volume of the gas goes to 0. And as long as you have atoms, which have mass, all right, you're never going to get truly to 0. So some strange things start happening when you get to really low temperatures. We'll briefly talk about that here in a little bit. But under normal conditions, i.e. temperatures that we're used to, Charles's law, as well as Guy-Lissac's law, works really well. One fun thing about Charles's law is liquid nitrogen, and you can take, for example, a balloon, which has a normal volume, place it in the liquid nitrogen, which is very cold at 77 Kelvin, which is minus 196 Celsius, and the volume goes way down. So remember, we're going from a warm temperature to a very cold temperature. Temperature goes down, the volume goes down, and you can see that balloon there. When you take it out of the liquid nitrogen, it's really shrunk down. If you let it sit around on the desktop for a while and warm up, it goes back to its normal volume, which is kind of fun. Charles basically studied balloons to figure out all these laws, which is cool. He was really interested in flying machines, the balloon especially and stuff. He's a fascinating person to read more about if that's anything you're interested in. So here's a question you might see. The volume of a gas is 235 milliliters at 25 degrees Celsius. At what temperature would the same gas have a volume of 310 milliliters? And we'll assume, by the way, that the pressure and the amount of the gas are constant, and there's 5 different temperatures there. Okay, the one tricky thing about this is that we have 2 volumes, and that's not a problem. But again, notice that it's in Celsius, and if you're going to make use of these kind of laws, you must convert things to Kelvin. All right, I'm just letting you know right now. So in this section, if you see a Celsius temperature and it asks about pressure or volume or whatever, convert over to Kelvin. So in this problem, first thing you'll do, 25 Celsius plus 273 will give you 298 Kelvin. That's the starting temperature here. You don't want to use Celsius. And then you can use V1 over T1 equals V2 over T2. So you'd solve for T2 in this case. But the temperature that's going to come out will be in Kelvin. So you have to then reconvert the Kelvin back into Celsius here to make sense of this answer. So if you do all that, you can see that first of all, I turned 25 Celsius into Kelvin, 298 Kelvin, no problem. Then the answer that came out was 393, but it's not Celsius, it's Kelvin. So if you subtract then 273 from 393, you'll get 120 with a dot showing 3 sig figs. That's going to be the temperature and stuff, where the volumes would be then 310 milliliters.
Pressure and volume are inversely related. Weight on the plunger of a sealed syringe increases the pressure on the air in the syringe. The air cannot escape, but its volume reduces under the pressure.
This is Boyle's law. Boyle was another scientist. Again, look at those dates. Wow, like 1600s, man. Just absolutely crazy. But Boyle studied pressure and volume. And what basically Boyle came up with is that the pressure times volume for one set of conditions equals the pressure times volume of a second set of conditions. So it's a little bit different. Scientists call this an inverse relationship. As one goes up, the other one goes down. So for example, if you increase the pressure, then the volume will decrease. On the other hand, if you shrink the volume down, lower the volume, then the pressure would go up, etc., etc. So notice that in the 2 graphs at the bottom, if you plot just regular volume versus pressure, it's a curve. And curve things aren't as easy to predict as linear things. So if you change the volume versus pressure to volume versus 1 over pressure, then you get a nice line. And you can predict that way quite accurately what's going on. So Boyle's law is pretty cool for predicting different things like this.
Quantity and volume are directly related. If we take 8 molecules of H2 and combine them with 4 molecules of O2, we get 12 molecules and a combined volume. If we then react the mixture, we end up with 8 molecules of gaseous H2O, which occupies the same volume as 8 molecules of any other gas.
Avogadro, of Avogadro's number, actually predicted that there would be some amount that was used, which is now called Avogadro's number. But he didn't actually calculate the number. He did realize from the study of gases that the volume of the gas does depend on the amount of gas. And so this video that we just showed on the right-hand side is awesome. It shows the reaction where water is being formed, and you can see the stoichiometry. 2 H2 are needed for 1 O2 to make 2 water. So initially, the H2, the circle, is bigger than the O2 because you need twice as many H2s, so the volume will be twice as big. The moles is proportional to the volume. But in that video, initially, when the 2H2 and the O2 were combined to make 3 moles of gas, the circle was even bigger. So you can see here how the volume is proportional to the moles or molecules. So mathematically, volume is proportional to the moles. So as moles goes up, the volume goes up, and as moles goes down, the volume goes down. So what you can say then from this equation is that V1 over N1 equals V2 over N2. So it is the amount moles N changes, then the volume changes, and that's kind of cool. We're also going to see, though, that volume is proportional to the amount that's there, and there's actually different numbers. On the right-hand side there, we've got 2 tanks with helium, and on the left-hand side, we have 1 mole of helium, and you can see the balloon is normal sized, I guess. If you have twice as much helium, which is what we see on the right-hand side, the balloon should be twice as big. So as moles goes up, the volume goes up, and vice versa. Pretty cool. If you combine pressure, volume, and temperature into one expression, you end up with what's called the combined gas law, and it's pretty handy. Now, P1 V1 over T1 equals P2 V2 over T2. So if pressure, volume, and the temperature are all changing, then you can use this expression. Now, you must use Kelvin for temperatures, definitely, but this is a nice way when you have more than one type of gas unit that's being changed at one time. If you also have moles that change, then you can use P1 V1 over N1 T1 equals P2 V2 over N2 T2. So again, lots and lots of different perturbations here. It just depends on which one you actually use. So wow, there's a lot of expressions, all right? You can see there's Guy-Lussac's law, and there's Charles' law, and Boyle's, and Avogadro's, and combined gas law, stuff like that. And I get kind of like, oh, like that person gets kind of fuzzy. I don't quite know which one to use. So I'll just let you know that the one that I use almost all the time is the one on the next slide, and it just combines all these other laws into one. You can use it to find these other laws we've talked about if you need it. So let's talk about the one that I use all the time.
A bicycle pump forces air into the confined space of the tire. As more air is added to the tire, the pressure increases. The tire's volume increases slightly, and the air becomes warmer. These observations are predictable properties of gases, and, as we explore in this chapter, they are described by the gas laws.
The ideal gas law is kind of the king of the gas equations. An ideal gas law is what I use almost all the time. I don't usually use the other laws. All of those laws can be derived from the ideal gas law if you want. And the ideal gas law, PV equals nRT. So P is pressure, V is volume, N is moles, and T is Kelvin temperature. R is the relation number that correlates with all of those right there. And it's a number you need to know / memorize to 5 significant figures. R is 0.082057 liters atmospheres per mole Kelvin. Now remember, if you see that -1, that means it's in the denominator. So you could write that as liters times atmospheres divided by moles, and kelvins. That's what the -1 means by there. They're in the denominator. You need to know R. You need to know it to 5 sig figs. Don't use less than 5 sig figs. Use the 5 sig value and you'll be good to go. The units are important though too, because it tells you what you need to use for pressure, volume, moles, and temperature. Pressure has to be in atmospheres, obviously, if you use this, because atmospheres is part of R. You also need to use liters for volume, Kelvin temperatures, and moles for amount. R, we're going to see, is very, very helpful for scientists, and we're going to use a different R value in a later chapter, the 8.3145 number. You can turn liters atmospheres into joules to get the joules per mole Kelvin version of the gas law. I will call the 8.3145 the energy R, and I'll call 0.082057 the gas R, all right? But they're both going to be important, but you just focus on 0.082057 for right now, because if you're pumping up your bicycle tire, you're changing the amount N, you're changing the pressure and volume of your gas, and all those things are going to affect the temperature. So you're going to need the ideal gas law because all of these things are changing, and we'll deal with the other version of R later. Here's a question where you can see the utility of the ideal gas law. And the question here says, how much nitrogen is required to fill a small room with a volume of 960 cubic feet? That would be feet cubed, which is an ugly unit, but notice that right next to it, 2.70 times 10 to the 4th liters. We want to fill that room with that volume to a pressure of 745 millimeters of mercury at 25 degrees Celsius, and we will need to use the R value here. So if you're going to use the ideal gas law, we're looking here for how much, which is moles initially. Moles equals PV over RT. So we're going to have all of our units in the right pieces. The volume's already set. It's in liters. We've got to turn Celsius into Kelvin always. So it's 25 plus 273 is 298 Kelvin. And the pressure then, we'll have to get that into atmospheres. So 745 divided by 760 millimeters of mercury per atmosphere, that comes out to be 0.980 atmospheres. So we're going to use liters, Kelvin, and atmospheres, as well as R, to figure out quantity, the moles N, and from there you can turn it into grams and kilograms, all that jazz. N equals PV over RT. When you figure out that, you want to solve for N. We're going to plug those different numbers in we had on the last slide. N comes out to be 1.08 times 10 to the 3rd moles. So if you wanted to tell someone how many kilograms or grams of it, you could totally do that. N2 is about 28.01 grams per mole. That's 28.01 times 10 to the minus 3rd kilograms per mole. So it's about 30.3 kilograms if that's what you're interested in. So this is how you would use the ideal gas law. It's great when you have multiple things changing like this one does. Pretty awesome. Gases are used quite a bit in chemistry for obvious and maybe not so obvious reasons. So sometimes chemists will talk about what's called a gas at STP, and STP stands for standard temperature and pressure. So the standard pressure is exactly 1 atmosphere, but standard temperature is 273 Kelvin, i.e. where water freezes. Now, if you happen to have a mole of gas at STP, you can solve for V. V equals nRT over P. You can put all that in. The volume of 1 mole of gas comes out to be 22.4 liters. So in the upper right-hand corner there's that little beach ball. That's something that's used sometimes at chemistry conferences. That represents 22.4 liters of volume. So in theory then, in that beach ball, you have 1 mole of gas. And if you had 2 moles of gas, you'd have twice that volume, 44.8 liters. And if you had half a mole, that would be half that volume, 11.2 liters, etc., etc. Now, of course, the temperature probably is not the freezing point of water, but it's hopefully close enough that it's not a big deal. Another part about this is that a mole of gas, any gas, will take up the same volume as long as you're at the same temperature. So it doesn't matter if it's helium, ammonia, or methane, or anything. As long as you have 1 mole of gas, it should take up about 22.4 liters at 273 Kelvin. Now, this is a question you might see. This is a Star Trek reference, so if you don't like Star Trek, you can just ignore it. But anyway, in one of the original Star Trek episodes, Khan, who was later in Star Trek 2, anyway, he tried to take over the ship, and they used what's called neural gas in that episode to stun them. But anyway, you don't have to worry about any of that. That's just me being silly, dorky, whatever, nerdy, whatever term. Anyway, Prophet back on. In this case, in this problem, Spock uses 2 moles of a neural gas to stun Khan and his henchmen before taking over the ship. So if you're at STP, what would be the volume of Spock's gas? Well, if you're at STP and you have 1 mole, it's 22.4 liters. If you have 2 moles, it would be twice that number, 44.8 liters. So you get the idea. Even neural gas, in theory, would work if you're at STP, all that kind of jazz. And remember, you're probably not at the freezing point of water all that much, but assuming you're close to it, then it's hopefully not too bad of a value. If you rearrange the ideal gas law slightly, it becomes really cool because you can relate the density of the gas to the molar mass of the gas. So bear with me here a little bit. PV equals nRT, ideal gas law, definitely. Let's put N over V on one side and P over RT on the other side. And why would you do that, Dr. Russell? Well, great question. Moles, N, equals the amount you have in grams, which we'll use for little m, divided by the molar mass, which we'll use capital M. So little m is the mass in grams of the gas, and big M is the molar mass of the gas. Now, this might seem really strange here, until you realize that little m, the grams, over the volume, mass over volume, that's a density of gas. And so if little m over big V equals the density of the gas, you can rearrange this expression. The density is little m over V, that equals Pm over RT, or what's usually used is this expression right here. It's called the evening dirt equation sometimes. Evening is PM, AM would be morning, PM is evening, and if you take out the R, DRT looks like dirt. So PM equals DRT. Now, why this equation is so helpful and why it's almost just as important as ideal gas law is that as the molar mass of a gas goes up, the density goes up. So in that picture there on the right-hand side, you have several balloons. We would say that the bigger molar masses are going to be on the bottom because those gases have a bigger density than air. They sink, all right, to the bottom. On the other hand, if you have helium or some light gas, those will float. Helium has a smaller molar mass, it'll have a smaller density. So it'll be less than the density of air and it'll float. So you can predict right away then if a gas will sink to the bottom or if it'll float. Gas, the gas around us, atmospheric gas, roughly 29-ish grams per mole, a little bit more than nitrogen. So most of the time then, the bigger gases with bigger molar mass will have densities bigger and they'll sink to the bottom. On the other hand, the smaller gases will float to the top. So here's a question you might see. It says, which gas has the greatest density at 25 degrees Celsius and 1 atmosphere of pressure? To answer this question, we're going to go back to the PM equals DRT expression. And we want the biggest D density here. And if they're all at the same pressure and same temperature, then what's going to affect the gas is the molar mass, the big M. So what you would do to answer this is you'd find the molar mass of each of those gases. So O2, 16 times 2 is about 32 grams per mole. Nitrogen, N2, about 28 grams per mole. Hydrogen is roughly 2 grams per mole. Carbon dioxide, roughly 44 grams per mole. I've dealt with these numbers a lot, so that's why I know them. If you have to figure them out from a periodic table, it's quite all right. But good old xenon, one of the heavier noble gases on the periodic table, is about 131 grams per mole. And that molar mass, that big M value, is a lot bigger than the other one. So we would say that xenon has the largest gas density of all those. We're just literally going to use the molar masses to figure it out. Conversely, then, the smallest gas density would be for hydrogen, H2. It has the smallest molar mass. That would be another thing you can do along the way.
Bromine vapor is roughly 5 times more dense than air. It can be poured from one flask to another. The density of bromine, like that of all gases, is directly proportional to the molecular mass of its molecules in the gas phase.
I promise to show you something really cool as long as you promise not to try it at home, okay? Okay. Now, everyone wants to know why my voice sounds higher when I inhale helium.
My simple fact is that helium is 6 times less dense than air, which means sound waves travel through it much faster, which makes my voice sound much higher. Now, the same effect can be achieved in reverse if I inhale something like
Sulfur hexafluoride, which is 6 times denser than air. I inhale some of that,
and my voice gets really low, although somehow I'm still funny. It's scientific!
Here's the secret. Hold on to it here like this. You hold on to that end. Okay, ready? Let's just set it in here like this. And we're gonna let go. Ready, set, let go. It's floating on a sea of sulfur hexafluoride.
So cool.
Does that look like magic or
Yes.
what? All right, so I want you to sink the ship. Ready? Reach down here and scoop up some gas. Does that feel dumb that you're scooping up gas? Now pour it in here. Did you see that? Do it again. Scoop up some more gas. Now slowly pour it inside. Do you see it? There it is.
Yes.
You sank it.
Okay, these are just a bunch of fun videos. So first of all, gases that are really heavy molar masses like bromine in the first video, you can actually pour them like liquids. It's amazing. Of course, we don't see a lot of this in our day-to-day life, but if you're using industrial applications, you might run into this. So they can be poured. And that led into the next video with a guy. I don't recommend doing this at home, but anyway, first of all, he sucked on helium, and you've probably maybe heard this. The voice gets really light and stuff like a chipmunk. And of course, I've never done that myself as a chemist and interested in science and exploring. But anyway, don't do this at home, kids. But anyway, helium will make your voice go really high. Now, in the last part of that second video and in this video right here, they're using sulfur hexafluoride, which is a very high molar mass gas. SF6 is pretty heavy. And so first of all, if you inhale it like that person did, your voice gets kind of dark and deep. And you can see from this last video here that you can actually float an aluminum boat on top of the SF6. That's a lot of SF6, by the way. And then the person was able to basically scoop up and pour the SF6 into the aluminum boat there and sink it, which is just crazy. So anyway, this is just fun with gases, and it's fun things to think about. Gases aren't all just things that evaporate and go up in the air and you never see them again. There's a lot of kind of cool things you can do. And now that you understand how density and molar mass is related, you can see what's going to happen. Kind of fun. Another useful equation that sometimes is used for molar mass and gases is this one right here, where molar mass of the gas equals mRT over PV. So again, M is the mass of the gas in grams, R 0.082057, temperature is the Kelvin temperature, pressure in atmospheres, volume in liters. This is the equation we'll use in lab, and sometimes if a question asks you to find the molar mass of a gas, this is a really nice way to do it. Now, you could still find N equals PV over RT first, and then molar mass would be grams over moles. There's nothing wrong with doing that. This is just like one-stop shopping. But anyway, lots of different uses of these gas laws, and you can just see a sampling of them here to see what possibilities exist out there.